Hi guys, welcome to Gatematic. In the previous two lecture we saw the current source inverter. In part A we saw for R load, in part B we saw for C load, and we came to the conclusion that in R load forced commutation is required, while in C load there is load commutation is possible. Why? Because for any particular value of time the load voltage is getting reversed, that is negative, and if load voltage will be negative, then on that time the voltage drop across any two thyristor will be negative, that is it will go into the reverse bias condition and natural commutation is possible. That is for C load. Now what I want to make the load commutation in resistive load. Okay, in resistive load I already saw that load commutation is not possible, here force commutation is required. But what I will do in case of resistive load, here R load is taken in part C, and in parallel with that we attach one commutating element, that is the capacitor. Okay, so what is the benefit of this attaching capacitor in parallel that we are going to see in this lecture? We can make this resistive load as a load commutating load. Okay, so here overall this combination is known as RC load, and we are going to see what will happen if RC load, parallel RC load is taken. Most of the guys are having confusion that why we are not taking the series RC load. See, there is nothing like RC load available in the market or in practical industry. So we can say that whole combination is RC load. Here capacitor I am connecting. Why? Because I have to make the overall circuit natural commutation or load commutation. Okay, so in order to make the load commutation I will insert capacitor, that is the commutating element, in parallel with the load, and the actual load is R load only. Are you getting this? Now you understood why we are taking overall combination of RC, that is the RC load. So let's get started. This is the circuit diagram of current source inverter, and how this current source inverter is working I already explained in the previous two lecture. So I am not going in detail that if from 0 to pi T1 T2 is conducting, T3 T4 is conducting. These all concept I already explained you in the previous two lecture. Also we can represent this voltage source in series with large inductor with one ideal current source whose value is Is, and this Is is constant. Here input voltage is something like this. Now in place of load, what I am attaching? I am attaching one resistor. This is the R load, and in parallel with R load I am connecting one capacitor as a commutating element. Okay, so whole combination I am saying that this is a parallel RC type of load, but actually this is R load only, and I am attaching the capacitor for natural commutation or load commutation. So let us understand how this capacitor is making the natural commutation or load commutation. We already saw that no matter what you are connecting the load current will remain as it is, as this is current source type of inverter. So load current I will get from 0 to pi Is, I naught is equal to Is, and from pi to 2 pi I naught will be equal to minus Is. These all things. Now see, from 0 to pi, this is my pi. If I'll talk about the degree axis, this is my pi. So from 0 to pi I am giving the supply across the load I naught, that is equal to Is, and that is DC. For full cycle it is AC, but for half cycle I am supplying the fixed Is value of current across this parallel RC circuit. Means if I will talk about the from 0 to pi, then the circuit will look like something like this. This is my Is, and this is talking about from 0 to pi. So now see, this is nothing but the parallel RC circuit, and in parallel RC circuit if you will find the voltage drop across this VC, then the voltage will be exponential in nature. In any unit step excitation, the RC circuit, the voltage will be exponential in nature. Fine. Now the point is whether voltage will lag behind by current or current will lag behind by voltage, that depends upon the RC load. Here RC load is taken, means across the capacitor the voltage will lag behind by current by angle some phi. As we know, for any RC load the current is leading the voltage by some angle phi. Means in other way we can say the voltage lag behind by current some angle phi, and exponential behavior we are getting at the output terminal. So if I will talk about the V0 is nothing but voltage drop across this R load, and this V0 and this VC both are in parallel. R and C are in parallel, so V0 will be equal to VC. So overall I can say the output voltage will be exponential in nature and it is lagging behind by current by some angle phi. So see, I am getting the output voltage lagging by current some angle phi, that you can easily see in this waveform. See, it is starting from this angle phi. This is my angle phi. Is it fine? And current is starting from 0 and voltage is starting from angle phi, means voltage is lagging behind current by angle phi, or you can say current leads the voltage by angle phi. That is the case of RC load in AC circuit. Got it? So the voltage, output voltage waveform I will get, that will be exponential and it will follow the exponential behavior from 0 to pi, because from 0 to pi I am supplying the DC current IS. Now see, from pi to 2 pi what is going to happen? From pi to 2 pi the current polarity is getting reversed, and when current polarity is getting reversed means this output voltage will be reversed, means it will be decreasing exponentially. Got it? Now I told you that here in case of resistive load I am attaching one capacitor that is responsible for natural commutation. Fine. So I need to make this circuit load commutated. So see here, from 0 to phi, this is my phi angle. So from 0 to phi, what is the output voltage? Output voltage is a negative. V naught is less than 0 from 0 to phi. So if V naught is less than 0, that means the polarity of V naught across it will be something like this. This is my plus and this is my minus. And from 0 to phi, which thyristor is conducting? From 0 to pi, T1, T2 is conducting. Fine. So T1, T2 is conducting in this time, and from 0 to phi, the polarity of voltage across it is something like this. So see here, if T1 and T2 is conducting, means I have to turn off this thyristor T3 and T4 prior to 0. If I will talk about the steady state, so see, this minus will come out here and this plus will come out here. So overall I can say this minus is coming out here and this plus is coming out here because of T2 is sorted. So this plus point will come out here. So T3 and T4 are getting reversed bias. So from 0 to phi I can say T3 and T4 are getting reversed bias, means it will turn off at a steady state. Are you getting this? So in this way we can make this circuit load commutated. Now from pi to, this is my pi plus phi. Okay, so from pi to pi plus phi, you can say that after pi, which thyristor is conducting? T3 and T4. I can say that, means T3, T4 is sorted at T omega t is equal to pi, and see, at omega t is equal to pi, or you can say at omega t is equal to pi plus, what is the output voltage? Output voltage is positive. So at omega t is equal to pi plus, or you can say from pi to pi plus phi, V naught is greater than 0. So V naught is greater than 0 means V naught, the polarity of V naught will be same as it is. So see here, when V naught will be same like this, then see, this T3 is sorted and T4 is sorted, means this negative terminal is connected with anode of T1 and this positive terminal is connected with cathode of T1. So this T1 will go into the reverse bias. Similarly, this positive terminal is connected with cathode of T2 and this negative terminal is connected with anode of T2. So the moment when T3 and T4 are getting triggered, then you can see that the voltage across T1 and T2 will be negative. That means it will go into the reverse bias, and when it will go into the reverse bias means it will turn off without attaching the any kind of commutation circuit. So here in this case load commutation is possible. Are you getting this? So in this way we have make the resistive load like load commutated by attaching one capacitor in parallel with resistive load. Got it? So that is the advantage of studying parallel RC circuit, and in parallel RC circuit we can make the load commutation possible. So if load commutation is possible means definitely we need to understand the circuit turn of time. What is the circuit turn of time? So circuit turn of time is defined the time for which thyristor is reversed bias. So see here, thyristor is getting reversed from 0 to this angle phi. I can say that. So from 0 to this angle phi, I can easily write this is my circuit turn of time. So I need to find the circuit turn of time of this type of circuit. So what I can say, I can write omega Tc is equal to phi. That will give me my circuit turn of time, and Tc is equal to phi upon omega, and where omega is the fundamental frequency. But The point is, if you don't know the angle phi, then you cannot calculate the circuit turn of time. Suppose in the question they have not given for what angle voltage is lagging behind by current, that is phi, then you cannot calculate the circuit turn of time in this case. But let me derive in this lecture, without knowing the angle phi you can calculate the circuit turn of time, so don't worry. Now, as I can say that this output voltage or voltage across capacitor is exponential in nature. From 0 to pi it is exponentially increasing, and from pi to 2 pi it is exponentially decreasing. Therefore, it is really necessary to find the voltage equation across this capacitor. Means suppose this RC load is taken, means it is really necessary to find the voltage drop across this capacitor Vc of t, and how much current is flowing across this capacitor Ic of t. Okay, I am interested in finding these things. So let me derive what the voltage across capacitor Vc of t and Ic of t. So what I will do, see, I can replace this whole combination with one current source, that is AC current source having value I naught is equal to Is from 0 to pi, and from pi to 2 pi I naught is equal to minus Is. So I naught RMS will be equal to Is only, that we saw in the previous lecture. So what I will do, I will remove each and every circuit and I will replace the output current I naught RMS is equal to Is, and in parallel with that RC circuit is connected. Okay, and this is my Vc of t and this is my output voltage, and you can easily say that output voltage and voltage across capacitor are equal. Okay, because these two are connected in parallel. So I am interested in finding Vc of t and Ic of t, and this is my voltage equation. So what I will do, I will use source transformation and I will make the voltage circuit. See here, this is current source in parallel with resistor. I can do the source transformation just by making voltage source, that is equal to Is into R. This is the source transformation, and in series with R, in series with voltage source R is connected, and this is my capacitor. Is it fine? And this is my Vc of t and this is my Ic of t. I can write like this just by doing the source transformation. So this is the series RC circuit. Now it is easier to find the response across the capacitor. So here initial condition, let us find Vc of 0. What is the value of Vc of 0? See, at t is equal to 0, Vc of 0 is nothing but minus of Vm. I can say that. So Vc of 0 is equal to minus of Vm, and Vc of infinite, I am talking about from 0 to pi only, but if it is for infinite duration, then Vc of infinite will be nothing but the source voltage. That we know, at a steady state capacitor will behave like an open circuit and all the voltage will drop across capacitor only. So here voltage source value is Is into R, so Vc of infinite will be equal to Is into R. Let me write this, that is equal to V. I am assuming that Is into R is equal to V. So Vc of t will be equal to, I know the equation according to network, Vc of infinite plus Vc of 0 minus Vc of infinite e to the power minus t upon tau, where tau is the time constant, that is equal to Rc. I can write like this. So finally Vc of t I am getting this much, that is V into 1 minus e to the power minus t upon tau minus Vm into e to the power minus t upon tau. So once I got the Vc of t, then I can easily find Ic of t. Ic of t will be equal to C dVc t upon dt. Is it fine? So differentiate the Vc of t equation, it will be equal to V upon tau e to the power minus t upon tau plus Vm upon tau e to the power minus t upon tau. Differentiate this dv by dt, you will get this one, and multiply it by c to get the value of Ic of t. So I can write Ic of t, I can replace this tau is nothing but Rc, so replace this Rc. So Cc will get cancelled out, and finally you will get in between 0 to pi, or you can say 0 to t by 2. Because this is exponential nature, increasing exponential nature, I am getting from 0 to t by 2 only, and from t by 2 to t the case will be different. I am interested in finding from 0 to t by 2 only, because I am interested in finding the circuit turn of time. So finally Ic of t will be this much and Vc of t will be this much, and we know this capacitor voltage is fluctuating between minus Vm to plus Vm, means from 0 to t by 2 the change in voltage is 2 Vm only. So I can write what will be the value of voltage across capacitor at t is equal to t by 2. At t is equal to t by 2, voltage drop across this capacitor will be Vm only, right? So I can write like this: at t is equal to t by 2, voltage across capacitor will be equal to Vm, and this is equal to V into 1 minus e to the power minus t by 2 tau minus Vm e to the power minus t by 2 tau. I can write like this, just replace time with t by 2 where t is the time period. Fine. Now separate this Vm term, it will be equal to Vm into 1 plus e to the power minus t by 2 tau. Now I need to find this V plus Vm. So what I will do, I will add V on both sides. I can write like this. So V plus Vm will come out to be, so this is my V plus Vm. So I can replace this V plus Vm, that is A is equal to 2V upon 1 plus e to the power minus t by 2 tau. So it will be equal to, I can write like this, and this is divided by R. Now this V, I already told you this V is nothing but, see here, this V is nothing but Vc of infinite. Vc of infinite, I assume that V is equal, that is equal to V, and that is given as Is into R. So I can replace this V is equal to Is into R. So R will get cancelled out, and finally you will get 2 times of Is upon 1 plus e to the power minus t upon 2 tau into e to the power minus t upon tau. So this is my final current equation from 0 to t by 2. Now from t by 2 to t, the current equation will be different. It is decreasing exponentially. So I am not interested in that. I am interested in only finding the current equation from 0 to t by 2. So this is my current equation I am getting in the form of Is, time constant, time period, and I can easily calculate because each and every parameter is given. Now once I got the IC of t equation in between 0 to t by 2, then I can easily find the load current I naught. Here this is the load current I naught, and load current is nothing but Is minus of IC of t. I can write like this, apply KCL at this point, you will get Is minus IC of t will be load current. So in this way I can find the load current also I naught of t will be equal to Is minus this equation. So this is equal to Is minus IC of t. Now subtract this IC of t, take this equation here and take Is common, it will be equal to Is into 1 minus 2 e to the power minus t upon tau upon 1 plus e to the power minus capital T upon 2 tau. So this is my load current equation from 0 to t by 2. Okay, so you need to mug up this, or you need to understand this. Maybe the question may be asked at t is equal to I think t by 4 or any time in between 0 to t by 2, what will be the value of current? Then in that case you have to apply this current equation, load current equation, and you have to find the current flowing in load. Okay, now let us find the circuit turn of time Tc. So I already explained you the concept of circuit turn of time. Circuit turn of time is defined the time for which thyristor is reversed bias. If it is asked that angle for which thyristor is reversed bias, then definitely it would be phi. And once we know the phi, then I can easily find the circuit turn of time, that is equal to phi upon omega naught. But what will happen if phi is not given? If phi is given, then no problem, you can easily find the circuit turn of time. But if phi is not given, then in that case you have to find the alternative. So I am going to derive the circuit turn of time. See, this is my time, I already explained you for which thyristor T1 T2 is getting reversed. Okay, so I can say when Vc of t will be equal to 0, then the time taken by capacitor to make the capacitor voltage is equal to 0 is known as circuit turn of time. See, at t is equal to 0, the voltage across capacitor is minus Vf, and at t is equal to Tc, the voltage across capacitor is 0. So I can say the time taken by capacitor to reach the voltage across it equal to 0 will be the circuit turn of time. I can say that. So see here what I will do, I will put the capacitor equation, voltage capacitor equation I already know, that is equal to V into 1 minus e to the power minus t upon tau minus Vm into e to the power minus t upon tau. This is my capacitor equation I was getting in between 0 to t by 2. Now from 0 to Tc I can easily say that capacitor voltage is getting 0. Okay, it is getting from minus Vm to 0, and the time taken by capacitor to reach the voltage from minus Vm to 0 is nothing but circuit turn of time. So I can write when Vc of t is equal to 0, then that time is known as circuit turn of time. I can write like this. So put Vc of t equation is equal to 0, then it will be equal to, so from here I can write Vm upon V is equal to 1 minus e to the power minus t upon tau upon e to the power minus t upon tau. I can write like this. Now at t is equal to t by 2, I already found the voltage across capacitor. So at t is equal to t by 2, what was the voltage drop across capacitor? At t is equal to t by 2, the voltage drop across capacitor is minus Vm. So I can write at t is equal to t by 2, Vc of t is equal to minus Vm. No, this will be plus Vm, because see here, at t is equal to t by 2, the voltage drop across capacitor is plus Vm, not minus Vm. So it is equal to plus Vm at t is equal to t by 2. So replace this t with t by 2 in voltage equation. It is 1 minus e to the power minus t upon 2 tau minus Vm e to the power minus t upon 2 tau. This concept I already discussed in this lecture. So see here, take Vm along left side, it will be 1 plus e to the power minus t upon 2 tau is equal to V into 1 minus e to the power minus t upon 2 tau. Is it fine? So from here Vm upon V will be equal to what? Vm upon V will be equal to 1 minus e to the power minus t by 2 tau upon 1 plus e to the power minus t by 2 tau. I can write like this. So V plus Vm I can replace, that is equal to 1 minus e to the power minus t by 2 tau upon 1 plus e to the power minus t upon 2 tau. I can replace V by Vm in form of time period and time constant. Now I will take this equation and this equation and I will solve these two equations. So it will be equal to 1 minus e to the power minus t upon tau. This is equal to this much. So separate this e to the power minus t upon tau on the right side. It will be equal to plus e to the power minus t upon tau. I can write like this, 1 is equal to this one. Now what I will do, I will take common e to the power minus t upon tau. Take common, it will be equal to this much. Fine. Just take e to the power minus t upon tau common, it will be equal to this much. Now if you will make denominator common, then it will be equal to 1 minus e to the power minus t upon 2 tau plus 1 plus e to the power minus t upon 2 tau. So in numerator e to the power minus t upon 2 tau will get cancelled out, and overall you will get e to the power minus t upon tau 2 upon 1 plus e to the power minus t upon 2 tau. So from here e to the power minus t upon tau will be equal to 1 plus e to the power minus t by 2 tau upon 2. Now take log on both sides, it will be equal to minus t upon tau will be equal to ln 1 plus e to the power minus t by 2 tau upon 2, right? Now take minus into log, it will be equal to t is equal to tau, and log will be reversed, it will be equal to ln 2 upon 1 plus e to the power minus t by 2 tau. Okay, so finally this is my circuit turn of time Tc, which is given as tau into ln into 2 by 1 minus e to the power minus t by 2 tau. So replace tau with Rc, so Tc will come out to be Rc ln 2 upon 1 minus e to the power, replace time period by 1 upon f, so it will be equal to minus 1 upon 2 Rc into f. So we know the frequency, we know the value of R as well as C, we can easily find the circuit turn of time, that is equal to Tc is equal to Rc ln 2 by 1 minus e to the power minus 1 upon 2 Rc into f. Got it? So this is really important, the question may be framed from this equation. However, in GATE exam, none of the question is framed from this equation. So that's all about the current source inverter. This much concept you need to understand in current source inverter, how I am making the resistive load as a natural commutation or load commutation just by inserting a capacitor in parallel. That is the motto of making this lecture. Now I am assuming that you have understood each and every concept related to current source inverter, and whatever the formula I derived, you should not mug up that formula, you should know how I am finding that formula. Okay, if you know this, then within a minute you can easily derive each and every formula related to CSI or any kind of voltage source inverter. Okay, for R load, for C load, each and every formula, it will take hardly 1 minute. But this formula, that is the last formula, circuit turn of time, you need to mug up this because the procedure is very long. However, if you understood the concept, then you can easily find the circuit turn-off time by using the concept also, but I would say that you should mug up this circuit turn-off time, the formula of circuit turn-off time. So in this way we have completed the inverter module, and now I would like to ask you, at the starting I told you that in all the three types of converter, whether it is rectifier, chopper and inverter, you will see that inverter is an easiest part. I told you at the starting. Now tell me in the comment whether you found the inverter as an easiest part or not. Okay, I explain each and every parameter related to inverter module, and now I am assuming that you know each and every concept. If you know each and every concept, then I can guarantee you that inverter you will feel that it is an easiest part in all the module, that is the rectifier, chopper and inverter. Also you have enjoyed the PWM inverter or not, please let me know in the comment below. It will boost me to make the next subject that my students are understanding each and every concept. Okay, so don't forget to comment, don't forget to share your views, what you want from my side. If it is possible, then I will make the next lecture also. There is nothing like I will not make. Okay, it depends upon my personal scheduling. Got it? So if you guys understood the concept, then please like this video, and if you're having any doubt, then you can ask in the comment below or join our Facebook group for doubt solving.